welcome.
Howdy, everybody.
I'm Amanda.
I'm Paul.
Hi.
Hi, guys.
You're really hard.
We're having technical difficulties already.
Okay. Okay, so we're going to get started talking about type systems, the good, the bad, and the ugly. So what makes a type system great?
What is it we're trying to accomplish? So the first thing we have to point out is we're trying to write better software. I think everybody here has that common goal. And Amanda and I, especially for those of you who were here 2 years ago when we presented, we sort of stacked the deck in our favor a little bit by saying we like type systems, but we like good type systems. Not all type systems are awesome. And to get back to the goal, what's the goal? The goal is to make the right thing the easy thing.
Yeah, I really want to be centered at the intersection of easy, straight, and lazy way. I'm not trying to do more work than I have to. I really want to be as agile as I can, and I want to get the most for my money, right? Like the most bang for my buck. I want the easy thing to be the right thing. And if I'm working too hard to make something work or to prove that it's correct, then I'm doing it wrong. So a great type system really is the cross between easy and lazy.
But not all type systems are great.
Yes, we said 2 years ago, not all type systems are great, and so we want to tell you exactly what we mean by that. How tired are you of hearing, Java sucks, I hate Java? Everybody says it all the time, and it's really hard to understand what they mean. Do they understand what type systems even are? It's hard to tell from that statement because everybody's been saying it for so long.
Okay, so what's, again, going on with the goal? There's a great quote from Yaron Minsky. We used it 2 years ago, we'll use it again. The goal is to make illegal states unrepresentable.
And really that implies the fact that you had to know what the states can be in the first place. What is an illegal state? Making sure that you've done the reasoning, you've figured out the logic to determine what are those illegal states, and then having the ability to make them unrepresentable.
Yep. So none of this is original thought. I don't think I've had an original thought in my entire life. This is all about type theory. It is. And there's a huge amount of formal literature out there. What we have here is called the Lambda Cube. The big beware sign basically means, you know, here there be math. We're not going to actually talk much about all of that, but that is the foundation for what we will talk about. We're basically trying to do a TLDR on type theory here.
So before we even get started with any of that, I've been going around the conference, pre-conference, talking to people and saying, what do you think about type systems? What are your opinions? Where are we even starting from to make sure we're on the right track with this conversation? And all I keep hearing is, I don't get the types of bugs that a type system will prevent. And really what that says to me is that this person lacks the knowledge to understand what a type system can do for them. So there's so much learning to do, and it'd be easy for me to say, okay, you lack knowledge, go read, but this stuff isn't documented in any digestible way.
Also, they may have experience with a type system, but it may be one of the ones that's on our bad list, or one of the ones that's on our ugly list. You know, we don't know.
Right. People understand that if you have a type system problem and you can't compile, you'll either have issues. If your issue is a type system issue and you're running in a dynamic language, you're going to crash, right? Not necessarily. You're doing it wrong at that point. If you think that crashing is the only problem, then you're doing it wrong and you don't fully understand what a type system can give you. This is Paul's quote.
Oh, yes, yeah, right. And I have to look more closely at it. Did I say that? Yeah. This is literally what I told Amanda. If the only type systems I was familiar with were Java, C, C++, or Go's, I'd be a Ruby programmer too.
Yeah, and this is exactly why we had so many crappy Ruby developers that are now crappy Clojure developers. Certainly, you can be an expert programmer. You can be amazing at what you're doing and use those languages. But I tend to think that if you're not thinking about the types, then there's a good chance you're not a great developer.
And actually, Anton van Straten, who's one of the editors of the current version of the scheme report, is fond of saying on Lambda the Ultimate that you have types in your head. You know? So even if you are programming in a dynamically typed language, you are in fact thinking about the same things that those of us who work in statically typed languages are thinking about. And why wouldn't you want to be able to express those in your language?
Yeah, and I met this really awesome woman last night who was telling me, she made this statement that if you own fabric softener, you can be a programmer. Because you have, for some reason, come up with some logic in your head that made you buy fabric softener. So she can take that idea to make you the type of person who can use your logic and put it down in code. So really, very cool.
Yep.
So all type systems not created equal.
Right.
So really, just right up front, this is not intended to be controversial. Everything we're going to tell you is a fact. That wasn't a joke. So it's not controversial unless, of course, you have some passion for any of these languages, and then you may be a little bit annoyed with us.
or a lot annoyed with us.
They're still facts.
Yes. We will, to be fair, we will offer some facts and we will offer some opinions about those facts. But I do want to put one stake in the ground, and that is that not everything is an opinion. There is actually such a thing as objective truth.
So let's dive right in and say, what does it mean for a type system to be good? What makes a type system good?
Right. And for you 80s movies fans, especially bad 80s movies fans, here's Howard. So what has he got? He's got a plate of curry. So this is all about the Curry-Howard isomorphism, and that is what we're shooting for when we talk about a good type system. And for those of you who aren't familiar with it, the fundamental thing that it claims is that a type is a theorem, and the implementation of a function of that type is the proof of that theorem.
Stop. Did you guys hear what he just said? Did you process that? That is so powerful. You don't think like that. I don't think like that. Nobody thinks like that. But if you sit back and think exactly what he just said, that is so important. That is so important to the way we write our code. If you're not thinking about theorems and proofs, totally makes sense. But you better have come up with the logic in advance of writing that in order to know what you're doing.
Yeah, it's perfectly valid for it to be an intuition. You don't actually have to be sitting there going, oh, I have this property of my software that I have to express this way, and I have to write the proof and all that kind of stuff. Some of us do that on purpose for at least some of our code, probably not all of our code. But it's okay if you don't think that way at all. Oh, yeah, right. The function type. The function type is logical implication. The arrow, I don't know how many people are familiar with the symbology of formal logic where there's a two-line arrow that means logical implication. There's a one-line arrow that means function taking one type to another type. Under the Curry-Howard isomorphism, they're the same thing. And so when you write a function, you can, and arguably should, think in terms of my type is actually a property that I want to express a proof of. The proof will be a function. What I've got here is a couple of Scala signatures, one of which expresses the notion of for all. It's universal quantification from logic. You want to say that something is true for every value of some type. And it's ridiculously easy to encode in Scala thanks to type constructor polymorphism. I'm not going to say anything more about that. We need to move on. But this is a good example of how you can express formal logic concepts in at least one statically typed programming language.
So in order for a type system to be considered at all good, it has to have the ability to express some types. This is essentially saying, earlier we talked about making illegal states unrepresentable. If you've thought about all of the inputs and outputs for your function, you can create some types that actually allow you to explicitly say, I can only accept this type.
Or that type. So my favorite example, the simplest example that I can think of this is errors as opposed to legal values. So with some types, you have typically an either type that expresses the fact that you've got some type that is only going to be, the value is only going to be of that type when an error has occurred, and then another type that expresses the fact that there will be a value of this type if there was not a failure. And that makes properly constructing code that handles failure cases in a compositional way where you're taking these building blocks and just assembling them together much easier.
So, and of course, having some types is awesome, but And we'll go around talking about type systems for the rest of the conference, but you need to understand that there's more important things than just the type system. You also have to have language features that are implemented to help you use your type system. Pattern matching, some types without pattern matching is essentially useless. You need to have the ability to quickly, concisely express what do I do differently in the case that it is X or Y.
Yeah, without some types and pattern matching, you're probably using the visitor pattern and emulating some types with, class hierarchies and all that kind of stuff. And we all know how painful getting the visitor pattern right can be and getting those class hierarchies right can be. If you haven't seen a statically typed language with genuine sum types and pattern matching, you're really missing out.
Yeah, Paul likes to say that this is like sushi. Until you've had it, you might not think it sounds very cool, but the moment you've had it, you want more.
Right. Yeah, you may not know you want it until you've had it. Yep.
So, and then another thing that you need in a great type system is product types. And most languages now get this, right? We need records and objects and tuples. The problem is the implementation. How hard is it to get to that? How hard is it for me to spin up a type quickly?
And do you have product types just by themselves without any of the baggage that tends to come along with the way product types are expressed in popular languages? Like, if the only kind of product type you have is objects, then you probably get inheritance along for the ride, and you may not want that.
And we've talked about something else that's really important. Another language feature that's really important is currying, the ability to do partial application on these things, understanding what you want to be able to be partially applied and what you want to make not possible.
Yeah, what are your tools for decomposing? If a product type is a collection of something of multiple other types, how do you take partial views of that structure? Language features outside the type system have something to say about that.
And then dependent types. Dependent types is like the final holy grail thing, right? Like you've probably been hearing about them quite a lot with Idris and maybe with Scala as well.
Yep. Yeah. In fact, Edwin Brady and Miles Sabin last year here presented a nice comparison of Scala and Idris, dependent types now and in the future, I think was the title. And immediately after us, Brian McKenna is presenting on Idris. Highly recommend checking that out. We'll talk a little bit more about dependent types as we go.
Yeah, and this is just quick syntax for a dependent type signature where you're checking the size of a vector. You're saying the size of a vector plus the size of another vector equals the size of your output.
And this is getting ahead of ourselves a little bit in the sense that we're going to talk about syntax because that's such an important thing about non-type system related qualities. But this, if you see the app signature here, it seems like it shouldn't be any more complicated than that. If you have a vector of size m and you have a vector of size n, then the result type had better be a vector of size m plus n. And why should it be any harder than saying m plus n, where you want that to be part of the type? The funny thing about dependent types is that's an expression, but it's not checked at runtime. It's not going to generate an assert. This code will not compile if you try to append a vector of size 3 and 2 in a code that needs a vector of size 6, for example.
So this is a very concise, overused example that in the small makes no difference, right? Like you're not going to write that. If this is your only code, you're not writing this because you don't care. But the syntax here is so simple that when you do put this in your code and you make it part of a bigger picture, then it does become very easy to reason about later, and it gives you safety that you don't get otherwise.
And that's, again, we're fans of compile time safety. Yeah, parametric polymorphism. Boy, it's almost, hopefully at this point, almost not worth talking about, right? Because we all know that Java got generics in Java 5, and C++ got templates, back in the mid-90s, I think it was. It's hard to think of a statically typed language that doesn't have parametric polymorphism. Go. Away.
So the question really is, what are you getting for free? If you're not getting anything for free, then why are you doing it in the first place? And type systems give you that. Parametric polymorphism seems like it should be default at this point. But it is really hard to implement, so you can't just say, go away. It's hard to implement. They may be released before they should have.
It's hard to implement. It's harder to add later. I think the Java and C++ experience was that designing a language without parametric polymorphism and then adding it later on a language that wasn't intended to support it is brutally difficult. So I'm waiting for the announcement from the Go team that, yep, we figured out, just like Java and C++, that we need parametric polymorphism. Ouch.
Yeah, ad hoc polymorphism is a nightmare. Having to go through and make a new implementation of every different type signature you want to support, a complete nightmare. So we also feel like it's really important for a type system to be extensible. And I'll use the example here where C# has the ability to use async. C# extended the language to have async. Whereas F# has the ability to make computational expressions where you can write your own async. You can write your own option type. If you have the same tools that the designer of the language had, you are so much more powerful.
Yeah, and here we have to offer a hat tip to a couple of the dynamically typed language communities. The Smalltalk and those Lisp communities have insisted since time immemorial, no power to the language designer that the language user doesn't also have. We agree completely.
Absolutely. So, okay, we're just getting to the bad. And you guys have an intuition about what's bad about a type system, right? You all hate writing Java. Right? Maybe not. Many of us do that for a living. However, you have this intuition. We want to give you a framework to determine what's good and what's bad.
Right. So yeah. So what's bad is mostly, whoops, we went black.
Ooh.
Yeah.
Sorry.
Yeah, we're suffering from a bad type system.
Back in the game, stringly type programming.
Yeah, stringly type programming. Yeah, go ahead.
So this is something that we all see. Paul and I were talking about this, and he's like, oh, it exists at the boundaries of programming, right? When you're doing I/O, you have tons of strings, right? And that's really where you want to be a little bit safer in most cases. But I have a gripe that this isn't just at the boundaries. This is all throughout code. Anytime I'm reading somebody else's code, when I'm hanging out with a client, checking what they've done, they're passing strings around. It's like, wait a minute, you have a type system, and you're not using it.
Yeah, I think, and we just talked about this before starting here, I think sometimes people who work even in good statically typed languages are embarrassed to just say type whatever equals string or type whatever equals int. In other words, to use type aliases to model something that, yeah, at runtime it's a string or at runtime it's an int, but to help the compiler out or help the compiler help you out by saying this particular type of string really belongs in this domain, this particular type of int really belongs in that domain.
So, huge pet peeve is this new culture that TDD is dead and static type checking is not required. I would like to assert that if you are operating under an SLA, if you have a service level agreement based on your code, you are being unethical by thinking both of these things.
I don't even see how you can believe them at the same time, personally. But okay. Yeah, I don't know about anybody else, but the majority of my career has been in e-commerce, which basically means writing a pile of code that shuffles around to other people's money. And I do agree with the assertion that, there is at least part of your code that, if it goes wrong, a bunch of other people's money falls on the floor. You do actually have an ethical obligation to avoid that. And type systems can help you avoid, good type systems can help you avoid that.
Bad type systems can help you avoid it.
Yeah,
it's
with
just
more
a
work.
nightmare
Yeah,
to do it.
Right. Right.
So we already talked about type aliases and how they're important. However, so languages can either be nominally typed or structurally typed, meaning that I could have a function that will accept either X or Y in this instance, if it's structural.
Yeah, based on its shape, yeah. The only consistently structural type system I know of is OCaml's, which is my favorite language right at the moment.
Static duck typing.
Static duck typing, yeah. So if a data structure has, X number of fields of types A, B, and C, and the function expects a structure with that shape, those fields A, B, X, Y, and Z, whatever, then anything with that shape will go through. So, if it quacks like a duck, walks like a duck. The problem, as Amanda pointed out earlier when we were talking, is that it is possible to get false positives that way. It is possible to get data that goes through that, the behavior isn't exactly what you want for that data. So you are sacrificing some safety with a structural type system.
Yeah, it's still worth having some safety. In most instances, this still adds benefit. So really the key to a bad type system is lacking connection between logic and your code. And some language designers, you can tell when you look at what they give you the ability to do, they didn't really understand anything about logic and code being equal.
Yeah, it's difficult or impossible to express and or not at the type level, right? It's just basic Boolean algebra, stuff that we do, at the term level, at the runtime level, day in, day out, every day of our lives. It's useful to be able to do that at the type level, and you've probably all seen horror code where people do that at the type level in various languages. That'll be part of our ugly conversation to some extent.
Jumping right into the ugly.
Yes.
So talking about syntax for a language really that's the core of where most developers spend their focus, right? Like this is why people love dynamically typed languages, because the syntax is so concise and super easy. There's not a lot to learn.
Yeah.
So we showed the Lambda Cube earlier. This is something that's very mathematical. You can read a PhD on it if you like. However, you probably don't want to, so Paul put it in a little table so we can see it very concisely what we're trying to achieve.
Yeah, I want to argue for dependent types because they're really just the final piece of the four pieces that you get when you intersect terms and types. What does it mean when you pass a term to a term? Well, that's called a function. What does it mean when you pass a type to a term? That's called inheritance or overloading. What does it mean when you pass a type to a type? That's called parametric polymorphism or generics or templates or whatever. What does it mean when you pass a term to a type? That's what dependent types are, and we saw an example of that syntax, at least a function signature earlier in Idris, and we'll talk about that a little bit more.
And we'll look at a different kind of syntax, that of dependent ML. You'll notice something interesting and new here called with type. This allows us to do dependent typing, which is phenomenally great. But if you don't know it and you approach this code, if you come as a new developer on a team that uses this code, what's the first thing you do? You delete all the extra crap that you don't know what it does. Right? Like, oh cool, I get to delete code. How many tweets have you read in the last month? I've been deleting code, I've been deleting code. Cool, did you remove some of your safety measures? Like, it was there for a reason. What was the programmer thinking? If I can tell what the programmer was thinking because the syntax is quite good, then I'm going to leave that code because I'm going to understand that it provides me with some safety. If I can't tell what the developer was thinking and I can't myself read it, gone.
So syntax matters. I think one of the things that we really want to communicate is that it's not sufficient just to have a really awesome type system. The rest of the language actually matters.
You can do really awesome things in Java.
Yes.
That's Java.
like this. Yeah, this is legal Java. This is a signature from a challenge that Tony Morris put forth to provide just the type signatures for a tic-tac-toe game that could never be in an illegal state. You could never have a board that you could move on that was from a finished game, for example.
I write Java on a very regular basis. I don't ever want to see that. I don't know what that does. That better be a very important piece of code that is people's lives or a lot of money is dependent on.
Right.
Or I don't want to have to go through the trouble to write it or ever read it. If the code's not going to change very much and it is very important to my code base, I may in fact go through the trouble of doing this. But I'm not going to follow that old adage that comments mean your code's not good. Right. I'm going to comment the heck out of that.
Yeah, exactly, and provide links to sources and all that kind of stuff. Yeah, this is the kind of stuff that in Java I only want to see protecting other people's money or protecting lives or what have you.
So,
oh yes, right. Is that Tim? Sorry. Yeah, that's a quote from Tim Sweeney, CEO of Epic Games. I trotted this out 2 years ago, and it was old then. It was 2 years old then. But basically, the point that Tim is making is this: that you can have all the expressive power. You can have a Turing-complete type system, like Scala does, like C++ does, like Haskell does. And if you aren't able to manipulate the obvious entities of your conceptual domain, strings, numbers, all that kind of stuff, if all you can do is inductive data types and get the compiler to do funny things by figuring out, typically through type inference, what to do with those inductive data types, that's a royal pain in the neck. There are libraries that have gone through that pain that you can use that are awesome. Shapeless for Scala is awesome. But if you look at the source code, it is unbelievably complicated.
So really, that led to something way more awesome, the kind of the holy grail, being able to use types and terms and kinds. Everything uses the same language.
Yep, and this quote now is from a paper by Tim Sweeney and 2 collaborators at Intel Labs about a new language that they have designed that collapses all the syntax for types, terms, kinds, all that into one syntactic category. So you can not go through the pain that Tim described 4 years ago.
Type level programming that's really easy with safety. This is so awesome. This is the reason people use dynamic languages, but with safety.
Right. You don't have to make all the compromises that, let me rephrase that. At some point, you won't have to make all the compromises that you currently have to make. Oh, faking dependent types, yeah. So in the meantime, folks like Oleg Kiselyov have made sort of a cottage industry out of taking existing statically typed languages, typically already fairly esoteric ones, the OCamls and Haskells of the world, and doing things that are purportedly only possible with dependent types in them anyway. The approach to this is something that was actually originally done in the 70s for the LCF theorem prover, and that's why standard ML was created. Standard ML was originally the meta language, ML, for a theorem prover. And you can still program that way in just about any programming language, statically typed programming language you care to name, including the kind of Java that we saw earlier. So again, it can be done. The question as to whether it's worth it is very, very domain dependent.
So most of the reason that people hate type systems is because of false negatives. You're spending your time changing the types, casting to change things that don't really affect the correctness of your code.
Yeah, that's...
If my compiler tells me I've done something wrong when logically in my own head I've done something, I know that what I'm doing is correct, I just can't do all the casting to make the compiler happy, that's a nightmare. That's what people hate about type systems, and that's what needs to be fixed.
Yeah, that's the overwhelmingly most popular complaint that I hear is, the compiler's just getting in my way, the type system's just getting in my way. And with the weaker type systems, that's probably true. You probably have a pretty good handle on what the actual behavior of this piece of code that you have in your head is going to be, and all you're worried about now is getting the compiler to accept it so that it can run and do what you already knew it was going to do. That, I think, is probably the best capsule summary of what a bad type system is. It does nothing really effective but get in your way.
Yeah, so you either go to a dynamic language where, in my own case, I wouldn't be able to sleep at night if somebody's money was depending on that. Or you use this and you can't sleep at night because you can't compile your code.
A double whammy.
So with type inference, type inference is a double-edged sword, right? I wouldn't write code without it because I depend on it. I love type inference. It makes my code really concise. I don't have to do type annotations. I want that. I love that. But I have this dichotomy. It's either incomplete but expressive or complete and weak.
Yeah, and from a correctness standpoint, there's also the issue that type inference gives you the most general type that it can infer, which from a correctness standpoint isn't what you want. What you want is the most specific type that is actually satisfied by the implementation. So I tend to use type inference, first of all, for noodling around. We talked about that 2 years ago, just the fact that you can sort of type and go, and if you're not too concerned about your types at that point, type inference will save you. Even when I scale up, though, what I wind up doing is relying on type inference for 90% of my code base, and then for the stuff that's really critical, I actually do spell out the types because I want more specific types than type inference is going to give me.
So there's a quote by Benjamin Pierce, the more interesting your types, the less fun it is to write them down. And this is unfortunately always true. But ideally, this wouldn't be the case. In a perfect language, this wouldn't be the case.
And I think as we get towards the more syntactically clean dependent type systems, that'll change a little bit because your type level programming will look just like your term level programming.
So you have to ask, what's the cost of proof? Which costs more to your company, which costs more to yourself? Not accepting a correct program or accepting a program that is incorrect.
Yeah, what's your loss function? What's at stake when your program misbehaves? What's at stake?
Another thing that drives people towards a language is popularity. And I don't know about you guys in high school, but I bet a lot of us were really weird in school, right? Like, so people probably would look at you and say, I don't really want to spend much time with them. They probably don't have a lot going on. They're not very popular. Now we're kind of the ones running the world, right? Like, seemed like we were going to be very popular if we were cheerleaders and jocks, but maybe not so much when it comes to real world importance.
Yeah, now that we're all adults. So part of the point here is just personality cults are not very helpful. They're not helpful in the technology world. They're not helpful elsewhere. I just had a conversation with a gentleman recently, bless his heart. I don't think he has spent a lot of time studying these issues, but he was talking about Go, and I recommended Rust to him. And he made the observation that the Rust community doesn't seem to be anywhere nearly as large as the Go community. That's probably true, but is that a really sound basis for comparing those two languages?
And that drives us right into culture. The culture of the culture surrounding a language, the culture surrounding a type system. I think like Clojure has an awesome culture in some ways. Like, they're always out learning more new things. They're book clubs. Like, these guys, they're the type of people who want to learn more and grow. But because Clojure has such a dynamic feel to it, because everybody wants to really rely on that, typed Clojure, how freaking cool, right? Who's using it?
Right. What's the uptake?
Yeah.
There's a huge cultural barrier there.
So there's also the idea for Haskell or statically typed functional languages. It's really hard to get into those groups because people won't listen to you unless you have your PhD in mathematics.
Yeah.
I don't want to be told to RTFM when I have to read through hundreds of pages of mathematical documentation in order to understand anything. So hopefully, talks like this, people who are out there trying to spread the good word are hopefully making it a little bit easier, not using the mathematical terms.
Yeah, this is not about being the smartest people in the room, which I don't think we are.
Not by far.
In any case. So there is that stigma, there is, type theory is a real serious mathematical discipline or theoretical computer science discipline. You don't have to be an expert in it to get the benefit of a decent type system, and especially with type inference and dependent types and a single syntactic category for types and terms, we can actually have a pretty pleasant experience with this whole thing.
Yeah, if you start to look at all the things that we said are good, all the things that we said are bad, and all the things that we said are ugly, if you matrix those together, what do you come out with? Really kind of yearning for something new.
Yeah, a lot of research still going on and still to be done, in all of this.
So we put together this informal hierarchy of type systems that you don't have to be a math major to read.
Well, we stole from a blog post.
We stole everything we've done.
we haven't had an original thought in our entire lives.
So just starting with an informal hierarchy, you have the stupid, barbaric, horrible type systems that we all complain about on a regular basis.
Yeah, they're lacking any of the positive features really that we started with in this talk, in this presentation.
But it's the first thing that you do when you want to write a type system because that's kind of a cool thing to do. Right. So you start with stupid.
Right. Basic correctness. This is not adding strings and integers, just really obvious, kind of simple, straightforward stuff like that. I don't have any time for languages that let me add strings and integers. I don't know about anybody else.
Most people here do. I'm just saying.
Okay, yeah, that's fine.
Then we go into expressivity, allowing you to really say what you want to say, kind of restricts you from doing what you don't want to do, making illegal states unrepresentable, generally.
Right, and maybe letting you express things in formal logic terms if you want, but maybe with some pain.
Yeah. And then you've got cock.
Yeah, right. Yeah, and to be fair, when you get to the dependent type world, I should point this out explicitly. Are you talking about a programming language or are you talking about a theorem prover? Is it a floor topping or a dessert wax? It's in the case of the Idrises and Agdas of the world, it's both, actually, on purpose.
Yeah, and I generally don't want to have to think in magic. I want to understand what's happening. So I think I don't necessarily need to be all the way to indistinguishable from magic. I want to be somewhere between those last two.
Yeah, well, hopefully they'll get less magical as some of the syntax and other non-type system issues get solved.
So then we go into the more formal way to look at a type system and to judge it. And you have the Lambda Cube. And this isn't nearly as hard as it sounds because we saw Paul's table earlier, and it uses all the same words. Using the same words plus a little bit of math stuff.
Yeah. These are just some categories. You can look at this stuff offline when the slides are available and the video's available. But this basically delineates the major features of type systems and where they sit on the cube. The cube expresses the fact that it's not actually a hierarchy, it's three-dimensional. There are three axes, and that's more than we really need to say right here, right now, I think.
Yep, but there are tons of speaker notes. Download the slides if you're interested in finding out where to find more. Hopefully we're giving you at least some ideas that you can walk away and Google. The hardest part is asking the right questions. If you don't know the questions to ask, if you don't know how to compare type systems, if you didn't even know it was a thing, hopefully this gives you an idea that you can in fact do that.
Right.
So just some last minute director notes. It's not all about the type system. However, type systems are really, really important. They're not created equal.
Right. There are good ones, there are bad ones, there are ugly ones, and it's an important judgment call as to when to choose to take advantage of them and when not to, or for that matter, when to change languages and change type systems.
We believe that it's unethical to not rely on a type system, to not work with a type system if you are working under an SLA.
Right. Whatever that means, other people's money or certain other conditions.
Lives,
yeah,
all
right.
the things that can be at stake with the stuff that we do.
Yeah.
And also the last bullet point really is important. Over the past few years, there's been a lot of new languages, and so I know a lot of people are starting to get burned out. Like, I can't learn all these new languages. Why do I want to? So if you're one of the people who thinks that we're done, we shouldn't have more languages, or we should just have one superior language that everybody uses, really you need to be paying more attention and thinking about where can we go from here.
And in the interest of intellectual honesty, we should say, we've talked a lot about dependent types, we've talked a lot about iterates. It's probably not production quality yet, to be honest. So I think what we're really talking about when we talk about this holy grail ideal dependent type system with a single syntactic category, blah, 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 is sort of where we hope to land a few years hence. We're pretty clearly not there yet.
Yep. Okay, so we're out of time. I'm Amanda Laucher. I work with Neo Technology, the company behind the graph database Neo4j. If you're interested in working with people who are awesome and thinking about this type of stuff and working with Scala or Java or any of our languages, please talk to me.
Yep, and I'm Paul Snively. I'm at Verizon on Q. We're a Scala shop as well. Come and talk to us. Thanks.